The first thing that we'll do in this lecture builds on what we proved last time. So in the last lecture, we proved that A5 is a simple group, that it has no non-trivial proper normal subgroups. We gave two proofs. The first one involved determining the conjugacy classes of A5 and noting that a normal subgroup is a union of conjugacy classes. So we determined the sizes of the classes and showed that if you have a union of conjugacy classes, including the identity class, there's just no way to add up the sizes of these classes to get a divisor of the size of A5 unless you take the trivial subgroup or all of A5. So the second proof is going to be the one more relevant to what we do in this lecture. How did that go? We suppose that n is a non-trivial normal subgroup of A5. And then we showed that n contains a 3-cycle in A5. Since n is normal, it contains the entire conjugacy class of that 3-cycle. And all of the 3 cycles in A5 are conjugate to each other. So you contain all the 3 cycles. But we also showed that the 3 cycles generate A5. So once you contain all the 3 cycles, you contain all of A5. So n is equal to A5. So what are we going to prove here? We'll prove that an is simple for all n at least 5. And the idea is going to be induction on n with the base case n equals 5. So in order to do the proof, we need this auxiliary lemma that I'll state and prove here. And what this lemma says is for any n at least 5 and any non-identity element sigma in an, it has a conjugate sigma prime that's not equal to it, where sigma I equals sigma prime I for some I. So just to give an example of what this statement means in action, let's take the 5-cycle 1, 2, 3, 4, 5 in A5. Let's take the conjugate by the 3-cycle 3, 4, 5. We get the 5-cycle 1, 2, 4, 5, 3. These two elements are conjugate to each other. They're certainly not equal. And they have the same value at I equals 1, meaning sigma of 1 equals sigma prime of 1. They both send 1 to 2. So that's the statement that we want. So here's the beginning of the proof. Let's just take some sigma in an that is a non-identity element. We'll write it as a product of disjoint cycles. And we're going to order those cycle lengths and let R be the longest one. So we can rename the elements of the set from 1 up to n. And if you relabel these elements, you're free to suppose that this cycle of length R is the R cycle 1, 2 up to R. So sigma is that one R cycle times some permutation pi, where 1 up to R and pi are disjoint, meaning that pi is some permutation, but it definitely fixes the elements from 1 up to R. So now the argument is going to break into cases when R is greater than or equal to 3, and then when R is 2. So I'll pause and erase and then finish the details of this proof. Let's finish this proof. We've written sigma as a product of this one R cycle, 1, 2 up to R, times some permutation pi that doesn't move any of the elements from 1 up to R. If R is at least 3, let's let tau be the permutation 3, 4, 5. And then let's take sigma prime to be the conjugate of sigma by tau. So sigma prime equals tau sigma tau inverse. Then you can check that sigma of 1 equals sigma prime of 1 equals 2. So they have some element that they send to the same place. But remember, we also need to check that they're not the same permutation. So to check that sigma is not equal to sigma prime, we find some element that they don't send to the same place. Sigma of 2 equals 3, but sigma prime of 2 equals 4. So what cases are remaining? Just R equals 2. Your permutation could be a product of just disjoint transpositions, that the longest cycle length that occurs in a product of sigma, and sigma is a product of disjoint transpositions, is R equals 2. So if there are at least 3 transpositions that occur in this product of disjoint cycles, then that means n is at least 6. And if you relabel the elements, you're free to assume that sigma is the transposition 1, 2 times 3, 4 times 5, 6. times a bunch of other transpositions. OK, so now let's let tau be the permutation 1, 2 times 3, 5. And same idea, take sigma prime to be the conjugate of sigma by tau. You can check again that sigma of 1 is sigma prime of 1 is 2. But these permutations are not the same because they send 3 to different places. So the last case remaining is r equals 2. So the longest cycle length that occurs in sigma as a product of disjoint cycles is 2. So it's just a product of disjoint transpositions. And the number of transpositions that occurs is not at least 3. It has to be even. So the only thing left is 2. So after relabeling the elements, you can suppose that sigma is 1, 2 times 3, 4. So now we'll take the conjugate by the permutation tau, 1, 2, 3, 1, 3, 2. And that gives us another product of 2 disjoint transpositions. And we can see that sigma is not equal to sigma prime. You can just check that they're not equal. But both of them fix 5. So because n is at least 5, these 2 permutations don't send any of the elements 1, 2, 3, 4 to the same place. But 5 is not involved in either of these, which means that it's a fixed point for both. OK, so how did this proof go? Once you have the statements, the idea is to write your permutation as a product of disjoint cycles. And there's this clever idea of working with the longest cycle length. So if that longest cycle length is at least 3, we can do one thing. And then in the case where your permutation is a product of disjoint transpositions, you have to work a little harder. But it's very explicit. You actually find which conjugate makes the statement of the lemma true. OK, so I'm going to pause and erase. And then I'll show you how to use this lemma to prove that an is simple for all n at least 5. Now let's use this lemma that we've proved to show that an is simple for all n at least 5. So the idea, as we said at the beginning of this video, is induction on n. And we already know n equals 5. So we're going to suppose that n is at least 6. And we're going to let an act on the set from 1 up to n in the natural way. So it permutes these elements. And one of the key ideas is now we're going to define a bunch of special subgroups of an. We'll let hi be the stabilizer of I for this action. It's going to be the subgroup of an that fixes I. So what does that look like? Well, now you have alternating permutations on all of the n-1 other things that are not I. So that exactly looks like a copy of a n-1. And by induction, each one of these is simple. So hi is simple for each I. This is one of the key ideas. So now we're going to proceed like we did in the second proof that A5 was simple. We'll just suppose that n is a non-trivial normal subgroup of an. And our goal is to show that n is equal to all of an. And how did we do that for A5? Is we showed that n contains 1 3-cycle, which means it contains all the 3 cycles, which means that it's actually equal to an. OK, so now we're going to use the lemma. So let's let sigma be an element of n that's not the identity. So we know there is one because it's a non-trivial subgroup of an. By the lemma, there is some conjugate sigma prime of sigma so that they're not equal, but they send some I to the same place. So since n is a normal subgroup, it contains all the conjugates of sigma. So it contains sigma prime, which means it also contains sigma inverse times sigma prime. And this permutation is not the identity. Why? Well, because it's only the identity if sigma prime is equal to sigma, and we know that it's not. So this is some non-identity permutation in n, but it sends I to I. Why is that? Because sigma prime sends I somewhere, and sigma inverse sends it back. So what does that mean? This is a non-identity element that's in n, but it also fixes I, so it's also in hi. The intersection of two subgroups is a subgroup. So n intersect hi we now know is a non-trivial subgroup of HI. What else is true about this subgroup? Since n is a normal subgroup in AN, when we intersect with HI, we get n intersect HI is a normal subgroup of HI. So what's true about n intersect HI? It is a non-trivial normal subgroup of HI. But we know that HI is simple. So the only non-trivial normal subgroup of HI is all of HI. So n intersect HI equals HI. N contains all the things in HI. But HI definitely contains a 3-cycle. So n contains a 3-cycle. And by the argument we described for A5, now we're done. So what are the big steps in this argument? You have to remember to work with this set of subgroups of AN that fix a given I. And then remembering this lemma is one of the key ideas, that you have to find some way to show something about how your non-trivial normal subgroup n intersects with these subgroups HI. And this lemma is sort of perfectly designed to show that that's non-trivial.